Okay, hi y'all. So we're going to work through the 4.2 notes right now. This is on the quotient-remainder theorem. So like I mentioned in the notes from 4.1, we're going to apply a lot of this stuff to integers and then apply it to polynomials because integers and polynomials share so many of the same properties. So before we start with the quotient-remainder theorem, we're going to practice long division, which is something many of you are probably like, how do I do that? And that's because we haven't done it in a very long time. So we're going to review long division. Later in this chapter, we will do long division with polynomials. So we're just kind of practicing, remembering how to do this and what all of the parts are called so that when we apply it to polynomials, we're a little more familiar. Okay, so for this long division right here, I know that looks like the square root symbol. We also use this symbol for long division. So that should be more like that. This right here means we're dividing 4566 by 200. So this is the actual division that's taking place. This is the setup for long division. And to do long division, so 200 is our divisor. So basically we're seeing how many times 200 goes into 4,566. To do that using long division, we ask ourselves, how many times can I get 200 into these first three digits? So how many times does 200 go into 400? We all know that that's 2, so I put my 2 up here. Then once 200 has gone into 400 twice, or 456 twice, that means I would figure out how much is remaining of that 456. So I would do 2 times 200, which is 400, subtract that out and see what's remaining. So 456 minus 400 is 56. Then I bring down this next digit and repeat the process. So then I ask myself, how many times does 200 go into 566 evenly? That would be 2 again. And then once it does go into it 2 times, what's remaining? So again, I would do 2 times the 200, so 400, subtract that out and figure out what's remaining. So 566 minus 400 is 166. At this point, I would repeat the process again. 200, how many times does that go into 166 evenly? It doesn't. So this means I'm finished. So all of my parts, we started with the divisor of 200. 22 would be the quotient, which is that whole number of times 200 goes into 4,566. I know that 166 is what was left over or remaining, so that's my remainder. And then 4,566, the number that's being divided, that is called the dividend. So that's a quick review of long division. We'll do another example here in a second. But we will continue using these words: divisor, quotient, dividend, remainder. Next, how do we check long division? So to check to see that this would be correct, there's a relationship between all of these things, the divisor, remainder, dividend, and quotient. To check it, what I would do would be to multiply 200 times 22. If I multiply that together and then add the remainder, that should all add up to my original dividend. So that should equal, I'm running out of space, 4,566. So that's how you would check it. So to check long division, you would do quotient times divisor. Quotient times divisor, add the remainder, and that should get you back to the original dividend. Okay, let's do one more practice of long division. This is a word problem. A farmer harvests apples, putting 50 apples in each bushel. He promised his daughter she could take any leftovers to her schoolmates. They harvested 3,087 apples. What is the maximum number of bushels that can be sold from that harvest? How many apples will the daughter take to school? Or in other words, how many will be left over? So if they harvested 3,087 and they use bushels of 50 apples. So basically we're seeing how many bushels will that consist of and how many will be left over for the daughter. So the setup for the long division, so 50 is the divisor, and I'm seeing how many times that goes into 3,087. So first you would see, okay, how many times does 50 go into 30? Well, none. So then you would go out one more digit, so 308. How many times does 50 go into 308? So it goes into 100 twice. So that means it goes into 300 6 times evenly. And then the 08, I can't get any more in there. So the absolute max times 50 can go into 308 would be 6 times. So once 50 goes into 306 times, then we need to figure out what's remaining. So you would do 6 times 50. So that's the 300. Figure out what's still left of that 308, which is 8. And then bring down my next digit and repeat the process. How many times does 50 go into 87? That's once. Once it does, multiply 1 times 50 and figure out what is remaining of that 87, which would be 37. Then I would repeat, but since 50 does not go into 37, this means I'm done with the division. So 61 is my quotient, and that's how many times 50 goes into 3,087, which means this is how many bushels were harvested, and then 37 left over. That's what's left over for the daughter to take to school. So that is what's left for the daughter. Okay, so there's a quick review of long division. We'll see that again in a little bit, but part of that is just understanding what all these pieces are. So the divisor would be 50, quotient is 61, remainder is 37, and the dividend is 3,087. So now we can jump into the quotient-remainder theorem. So the quotient-remainder theorem basically says for any number and d, a positive integer, you can divide n by d, and there's going to be some unique quotient and some unique remainder. It's just a very simple way of saying pick a number d or n and some divisor. I can rewrite n as that divisor times some quotient plus a remainder. So n and d and q and r are all integers. And we'll look at a few examples so you see how this is applied. The one thing we need to note is that remainders, remember this remainder here, so if we go back to this apple problem, has to be less than the original divisor. So if this was more than 50, I would just continue the long division. So the remainder definitely has to be less than the divisor. So r is less than or equal to the divisor. But also the remainder has to be positive. So that's an important piece of this that we'll see later in this section. So it has to be greater than or equal to 0. It doesn't make sense to have a negative amount of something left over. So let's apply the quotient-remainder theorem here. So if I'm talking about my number n being 8,714 and the divisor being 73. So I'm going to use this relationship here to start working through this problem. I want to find the quotient and remainder using the quotient-remainder theorem. So n is 8714, and that equals 73. I'm going to divide it by 73. 8714 equals 73 times some quotient plus some remainder. And our job is to find out what that quotient and remainder are. So the quotient is just going to be the highest whole number of times 73 goes into 8714. So to figure that out, whoops, all we have to do is do 8714 divided by 73. It's going to be a decimal because 73 isn't a factor, but this 119 point whatever. So this means 119 times is the whole number of times 73 can go into 8714. So my quotient is going to be 119. Then we just need to find the remainder. So if I want to know what's left over, well, since 73 goes into our 8714, 119 times, then there's some left over. I would just do 73 times 119 and see how close that gets me to 8714. So 8687. So I just need to figure out what's left over between my original dividend, 8714, and that number right there. So I would just do 8714 minus that value and find that remainder of 27. So Q is 119, the remainder is 27 in this example. And then to check that, again, all I would have to do is just plug this in. So I would do 73 times 119 plus 27, and it gets my original value of 8714. I'm going to do one more quick example because I only had one of these. So this new example, same idea. If n equals 413 and D, my divisor is 21. What are my Q and R values? So again, I'm just the quotient. Anytime you're told to use the quotient remainder theorem, this is the setup here. So n 413 equals 21 times something. That's my quotient I need to find, plus some other remainder amount left over. So again, I'm just going to take the calculator. We're going to do 413 divided by 21 and see how many whole times 21 goes into it. So 19. And then I still need to figure out, so this is my Q. Q equals 19. What's left over? So I would just figure out what that 21 times 19 is. Whoops. That's 399. So then we would just do 413 minus 399 to get my remainder of 14. So Q quotient is 14 or 19. The remainder is 14. Okay, one more example here. And this is a special case because look at the value of n is a negative value. So we want to know if n is negative 16, then I'm dividing that by 3. My divisor is 3. What is my quotient? What is my remainder? So we know that 3 times negative 5 is negative 15. So that goes into it. And then to get to negative 16, I would have to add negative 1 or subtract 1. However, remainders can't be negative. They have to be between 0 and the divisor. So R needs to be between 0 and 3. So negative 1, this doesn't work. So what that means is anytime you have a negative n value, so think about it on a number line. So we got to negative 15 here up above, and then we had to subtract 1, R equals negative 1, but that's not okay. We can't have a negative remainder. So basically what you have to do here is instead, whoa, I wrote negative 15 there. Sorry. Okay, that should be negative 5. We know 3 times negative 5 is negative 15. But our remainder has to be positive. So what that means is we have to go one more past negative 5. So we would have to do 3 times negative 6, which is negative 18. So then we're on the number line, we're back here. That way, when we go back to negative 16, our remainder of positive 2 works. So that would be positive 2 there. So Q is negative 6 and the remainder is 2 here. You cannot have a negative remainder. So if n is negative, you basically have to pass it, go farther past it on the number line when you're finding out what your quotient is so that your remainder is positive. So this is a common mistake I see. So make sure you keep an eye out using quotient remainder theorem when that n value is negative. Okay, on to the next page. Now we're going to apply this to polynomials. So like I said, polynomials and integers have a lot of the same properties. So same ideas. Instead of n, d, q, and r, Now we have n of x, d of x, q of x, and r of x. So those are just all polynomials now. So for every polynomial n of x and d of x, as long as they're not 0, there exist unique polynomials q of x and r of x such that n of x, so that original polynomial, can be broken down as the divisor d of x times the quotient polynomial, so q of x, plus some remainder r of x. And then just like our remainder for integers, the remainder could not be less than the divisor. Well, how do we gauge whether or not a polynomial is less than another polynomial? So that doesn't really make sense. What it really matters is the degree of the polynomial. So the degree of the polynomial, r of x, the remainder, has to be less than the degree of d of x. So the remainder has to have a degree that's less than the remainder of the divisor. Also, r of x could just be the 0 polynomial. The 0 polynomial. Okay, so let's do some polynomial division. So let's look at this. Use long division to find the quotient and remainder. So here, this would be like our n of x. We're dividing that by x minus 1, which would be the d of x. And we want to know what is that quotient and what is that remainder so that we can set up this relationship right here. It says use long division. Now, we reviewed long division, but not long division with polynomials. We haven't learned that yet. In Math 3, we learned a special way of dividing polynomials using polydoku. So we're actually going to use polydoku. We will use polynomial long division. I will teach you that in this chapter. Until then, we will use polydoku. So if you remember polydoku, we want to figure out, we used those area models to figure out how to do this. So what we want to know is, I'm trying to get my view right here. So I want to know if I take 3x squared minus 2x plus 1, and I divide out x minus 1. So x minus 1 times some divisor polynomial, quotient polynomial, plus some remainder. So I want to know x minus 1 times what is going to give me 3x squared minus 2x plus 1. So the setup for polydoku, if I'm taking, again, area model, so x minus 1 is one polynomial, and I'm going to multiply that by this other polynomial, q of x, which is going to be this polynomial up top, to equal 3x squared minus 2x plus 1 right here. So I just have to figure out basically what is going to go in my area model to have this product, or what is going to go up here, this other dimension, to have a product of 3x squared minus 2x plus 1, which will add up, everything in here will add up to that. So if you remember from last year, this first term right here, x times whatever is here has to add up to that, or multiply to that 3x squared. So we start by putting the 3x squared here. Then x times what is 3x squared? Well, that means this dimension has to be 3x. But if that's 3x, and I already know this is negative 1 right here, that means I can get that product, which is negative 3x. Then we look back at what our original dividend was. I wanted it to be negative 2x right here, but right now I have negative 3x. So then I need to adjust my area model, this area right here, so that I have negative 2x's, which would mean I need to add an x back in. Then if I know this is x, and this is x, and this has to have a product of x, that means this would just be positive 1. And if that's positive 1 and that's negative 1, then I know this area is negative 1. And then we go back here, but I wanted positive 1 in my dividend. So what do I need to add in my area model to have that positive 1? That would be plus 2. And then I can't multiply x by something to get 2. So what that means is that 2 is actually my remainder r of x. And my quotient is 3x plus 1. So that means I could rewrite the whole relationship here is 3x squared minus 2x plus 1 is the same as x minus 1 times the quotient 3x plus 1 plus 2. So we've got our remainder and our quotient. Okay, so that's a quick review of Polydoku. You've got cube of x, 3x minus 1, remainder 2. So remainder, technically 2 is a polynomial, it's just degree 0. All right, so now I'm going to show you my favorite part of this, and that is the relationship between this whole thing as a function and its graph related to the graph of its quotient. So if you graph the original function, so take a look at my screen here. 3x squared minus 2x plus 1 divided by x minus 1. So I can look at the graph of that. It'll draw it for us here. Kind of funky. And then if I graph the quotient in the same window, so graph 3x minus 1 in the same window. 3x plus 1. Oops, you guys, sorry for all my little mistakes. Okay, 3x plus 1. So when I graph that, watch what happens. So that 3x plus 1 is the equation of the oblique asymptote, or oblique just basically means diagonal, not horizontal, not vertical. Oblique asymptote of my original function. If I treated this whole thing as a function, this quotient is the asymptote on that graph, which is super cool. Why is that cool? So first of all, what do we notice? So the quotient is the equation of the oblique asymptote. Oblique asymptote of f of x. Okay, why does this matter to us? Well, that's because if I know the equation of the oblique asymptote, so asymptotes always, oblique asymptotes and horizontal asymptotes always indicate end behavior for us, meaning what happens at the far positive and negative ends of the graph. So if we look at the, let me graph a quick sketch of this. So here's my graph, quick sketch of this graph. So if I'm talking about end behavior of this function, basically I want to know what happens as x approaches positive infinity. So as x gets larger and larger and as x gets smaller and smaller, what's going to happen? Well, that oblique asymptote, which goes like this, functions always approach whatever the asymptote approaches. So if I'm not able to look at a graph of this, but I can at least get the quotient and I know what the graph of the quotient looks like, then I know what the end behavior is doing. So my point is, I don't know, before we graphed it, we didn't know what this graph looks like, but I do know what the graph of 3x plus 1 looks like because I could sketch that pretty easily. And this is going to indicate the end behavior of f of x. So since a line 3x plus 1 just looks like this, I know that my function is going to approach infinity just like this does as x gets larger and larger. So if I write my end behavior, so quick review of function notation, the limit of f of x as x approaches infinity is going to do the exact same thing that its quotient does, which is approaches infinity. Same thing as x approaches negative infinity, the limit of f of x as x approaches negative infinity. Well, whatever my quotient does, it's approaching negative infinity, so my function will as well. Okay, I'm going to do that, kind of recap that process on this next example. So without using a graphing calculator, we're going to describe the end behavior of this whole rational function. So again, I don't know what the graph of this looks like, but if I can figure out what the quotient is of the numerator divided by the denominator, that should be, so if you think about something of degree 2, if I'm dividing that by something of degree 1, my result will also be first degree. And I know that first degree polynomials are just lines, and I know how I could sketch those without a graphing calculator. So what is the quotient? So that's what we need to know when I divide. So we will divide 2x squared minus 5x plus 4 by x minus 3. In other words, x minus 3 times what will give me that numerator. So again, 2x squared is what this missing dimension and x minus 3 have to multiply to. So I would put 2x squared here. So x times what is 2x squared? Well, that has to be 2x times x to be 2x squared, which means I know the area of this, that's going to be negative 6x. Then I look back at my original numerator here, I want negative 5x. So to get that with my negative 6x, I need to add in a positive x here. Then I know that x times something is x, which means that something is 1. Then I know this has an area of 1 times negative 3, which is negative 3. I did not want negative 3, I wanted 4. So that means I need to add 7. At this point, this degree is less than this degree, so I'm done. So I know that I'm finished here. So my quotient is 2x plus 1. The quotient is what is going to help us figure out what the end behavior of this function does. So this graph I do not have in front of me, but I do have the equation of its oblique asymptote, which is 2x plus 1. So I know it has a y-intercept of 1, a slope of 2. So it looks something like this. So all I know is the asymptote looks like that. Without even graphing the entire g of x, I know that it's going to approach whatever these ends approach. So I know the end behavior of g of x just by looking at its oblique asymptote. So I know that the limit of g of x as x approaches infinity does whatever this does, which is approaching infinity as well. And I also know the limit of g of x as x approaches negative infinity, because it's doing whatever this is doing. And then we could just check that on the graph if we want to see what that looks like. So we can graph 2x squared minus 5x plus 4 divided by x minus 3. Let's see what that graph looks like. And then I can graph my quotient 2x plus 1. And we'll see that same relationship here. Whoops. So we see that oblique asymptote. The function is going to get closer to the asymptote at the far ends, looking at that end behavior. So that's why we really only need to know that oblique asymptote, which is the quotient, to figure out the end behavior. So we don't even need the whole graph of that, which is super awesome. Okay, that's it for 4.2. And that's it. Okay. See you next time.